Good morning and welcome to our continued discussion on analyzing functions and graphing. Now we have every time I'm going to review the graphing steps, where we are in that discussion, what still needs to happen, and so on. Because it's good to have a big picture. Well, I prefer to know where I am in the grand scheme of things. We have our warm-up where I just identify the function if I can and find the y-intercept. It's always nice to make some progress. Then we had our second step, asymptotic behavior, where I look at long-term behavior. Are there asymptotes? Maybe I care to know what happens close to the asymptotes. Maybe I just have some arrows to be refined later. Either way, I want to identify asymptotes, identify long-term behavior, see in that sense what this function is doing. In no way can I get a good picture of the graph at this stage, but it is an important step that I have to do. Next, we want to know where is the function increasing and where is the function decreasing. So I'll call that increasing, decreasing behavior. And then we have a couple more steps to go, but one thing at a time, right? Okay, so increasing, decreasing behavior. If I have a function, let's call it f of x, we officially say it is increasing on an interval. Let's call the interval x1, x2. Can really be anything. Let's call it a and b. No, yeah, let's call it a and b actually. That's going to be better. A to b. If I take two x values in this interval and I compare the y values, the function values, let's have a picture. Let's have a saying and writing different things makes it confusing. For any two x values in this interval, let's just see what happens. I don't care what happens outside of the interval. Let's suppose I have an A and I have a B interval. This is my window. Nothing outside matters. If I compare any two x values and the y values, the points need to be going up in terms of the y value. So the second one needs to be bigger than the first one, or the first needs to be smaller than the second. I need to be going up in some way. It could be wobbly, but from A to B, I need to be going up. One of these endpoints, one of the x values could be the very end point. I still need to go up towards it, so increasing. So it's not a super complicated concept. Just picture the graph. I have to go uphill. I have to go up, increasing. And then I can do the same thing for decreasing. Just for the sake of being complete, I write out the definition, but that's never something that I'm going to ask you to state formally. It's good to see how the language looks. Function f is going to be decreasing on some interval a to b if I compare the function values between any 2 points, x1 and x2, in this interval. Could be the endpoints, could be interior points, doesn't matter. I need to be going downhill in one way or another. Could be slow. You see up here it's slowly going down, then it speeds up a little bit. Either way, it's going downhill. So if I compare 2 points, any 2 points in this window, in this interval, the first one needs to be greater than the second. Now again, look at this, don't look at it, just understand what we mean by increasing and decreasing, downhill, uphill. There could be many different versions of going uphill, right? Of having a function be increasing. For example, I could go really slowly and then increase and get steeper and then maybe slow down again. Lots of things can happen. Regardless, in this window, what do the tangent lines look like? I have a little flat guy here. He's not perfectly flat. He is still going up. And then he's getting steeper, 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 then maybe slowing down a little bit, heading towards flat in this example. But for all these tangent lines, all the tangent lines have positive slope values. Might be small, might be big, but they all have positive slope. So what does that mean? Well, what is the slope of a tangent line officially called? Slope of a tangent line. Does anyone remember what is our fancy word for slope of a tangent line? It's the derivative. And I have a name for the function, so I'll just write my f prime notation. Positive, positive. Now, there is a little technicality that I just want to get out of the way because so many books, they just don't do it right. Or they glance over it, they don't address it, and it, to me, has become sort of the elephant in the room. We need to talk about these things. So let's do something like this, where I have a point where it's perfectly flat, for example. And then it picks back up. This graph is still increasing throughout. Because if I compare any 2 points, it could be this flat one, it is going up. If I compare anything on either side, it is going up. Everywhere, comparing 2 points, they're still going up. So technically, this has to be a greater than or equal. Technically. With the exception that I have a perfectly horizontal line throughout, well, then I wouldn't even bother with this increase and decreasing question anyway. So I like an equal sign as an option there to cover this possibility, which does happen. If you think about, for example, the basic polynomial x cubed, it has this property. Let's look at y equals x cubed. I know what the graph looks like, or I should. It is perfectly flat in the center. Yet from left to right, compare any 2 points. Any 2 points. I'm always going up. It's increasing for all x values. Yet there is a flat spot. And then it picks back up. And that's okay. It doesn't change the increasing nature. So technically here we have equal signs. And there is a distinction between increasing and strictly increasing, where strictly increasing doesn't allow for this. We're not interested in that. We're going to have an equal sign. But the nice thing is, it's the derivative. The derivative being greater than or equal to 0, and I'm increasing. So it's a very simple check to make. I just need positive or not negative slopes. Here it's going to be the same. decreasing, I'm just going to have I'm going to be okay and allow the equal sign for reasons I just said. Even though it's sometimes going to be flat, my slope lines, they're always going to be negative. So all slope values in a section like this will be, all slope values are negative or 0, meaning that my derivative needs to be less than or equal to 0. So again, for increasing decreasing behavior, this means that I just need to check where is the derivative. I'll just relax and say always positive, negative, understanding that 0 is okay. Where is the derivative positive? Where is the derivative negative? And then I'm going to have the answer to where it goes uphill, where it goes downhill. So it's actually quite simple. Did I do it on this page? Right. When we looked at asymptotic behavior, I looked at the function. When I look at increasing decreasing behavior, I'm going to now look at the derivative. So let's do some examples and see what there is to see. Well, I have this guy. Might as well finish this guy. The derivative, oops, there's no need for a little denotation, is going to be 3x squared. And you see this is always going to be greater than or equal to 0 because take any negative x value, the square is going to make it positive. In the case where x is 0, then I have a 0 slope, but I satisfy the requirement of being at least 0, so I'm increasing everywhere. But of course, this function isn't very interesting, right? It's a basic function. I already know everything about this guy. We want to go through our types of functions, at least most of them, to see how do I handle this in more complicated situations. So let's start with the easiest one, which is a polynomial. Now, you can very easily get situations where the polynomial doesn't factor very nicely. So I just want my specific example to have a good first example. This is zoomed out. I have it on my other screen, but it's so zoomed out I can't even see it. Okay, there we go. X cubed plus 3x squared minus 9x plus 4. All right. I don't know what that looks like. I have an idea of something based on x cubed. It has a couple of turning points maybe. It's not too wild, but I don't know exactly. Okay. So we would have maybe in a larger graphing question, we would have already done asymptotic behavior. We would have seen that the graph goes up far to the right, down far to the left. We have a y-intercept of 4, but we don't have much. Increasing decreasing behavior will really start to fill in the shape of the graph. But for that, I need to find the derivative. So I have 3x squared, all basic properties, plus 6x minus 9. Now I want to factor this. And I can start by taking out a 3. That's going to help me a whole bunch. And we're not going to make the factoring super complicated. We've done in pre-calculus, you've done a ton of these things. There's no need to test you on the most difficult factoring, because that means I have to remember all those things as well, and you very rarely use them. But here I kind of need to. So hopefully this will work. It's going to be a plus 3 and a minus 1. Okay. So now I'm going to use the table that I introduced last time here again. So what I'm going to do maybe first, just do it on the side here, is identify where this derivative is 0. Well, because I have it factored, it's actually something I could just read off. It's when any of the brackets equals 0, which is going to be when x equals -3 or 1. So in this factored form, super easy to find where the derivative is 0. Those are going to be the numbers that I'm going to mark off on my number line. Then on the left, I'm going to list every factor that I see in my derivative. Whether they're crucial or not, get into the habit of listing everything. Now these numbers, -3 and 1, split up my x values into 3 separate intervals. 3 is always going to be positive. So it doesn't really do much, but it is contributing something. I don't want to leave it out. Sometimes it really matters. X plus 3 is going to be 0 when x is -3. We've done this before, and I've asked you to be comfortable with why it's going from negative to positive. X minus 1 in isolation is 0 when x is 1. It's also going to go negative to positive. Please double check. Don't look at this and say, oh, they're always negative to positive. No, you have to look and be sure. If this looks a little different, it could very much be different. Okay, so just remember this is the derivative. This table is now set up to say where the derivative is positive or negative, because that's exactly what I need to be able to say something about increasing, decreasing behavior. So the table looks the same, but now it's applied to the derivative, not the original function. So when x is -3, x plus 3, this bracket is going to be 0, and it's going to make the whole thing 0 because I'm multiplying. When x is 1, the second bracket is 0, making the whole thing 0 because of multiplication. For the first interval, I have a positive and 2 negatives being multiplied together. My answer will always be positive. For the middle interval, I have 2 positives and a negative. My answer will always be negative. For the last interval, positive. I cannot stress how useful this table is. I use it all the time, even still after I've done thousands of these. So there must be something to it. Many books you'll see, they just look at the last row here, and then you just have to hopefully do everything correct in terms of guessing to find the last pluses and minuses. Yes, this last row is the only row I'm really interested in moving forward, but where do they come from? They come from an interaction of the individual factors. And because those factors in isolation are super easy to look at, I can just look at each one quickly, then combine them and know exactly where the end results come from. So it still has benefit. If I don't write down this middle, then I could very easily make a mistake, and the middle is not hard. So what does this mean? I'm going to leave a little space here. I'm going to write something in a second, but I now want to write a full sentence saying where the function is increasing, where the function is decreasing. Now notice that this sentence refers to the function. Even though I'm looking at the derivative, I am making conclusions, making statements about the function, the original. F is increasing on, first interval is -infinity to -3. Infinity always gets a round bracket. -3 gets a square bracket because there is a point, but nothing past that. Then I'm going to turn downhill. 0 is okay. Downhill? No, that's not increasing anymore. And of course, I also have the last interval, 1 to infinity. Now officially, when you merge these two, it's by a union symbol. But if you you've never seen that before and it makes you uncomfortable, I just need you to list all the intervals. Doesn't matter. And then my function is decreasing. There's still some new things happening here. Let me know if you have any questions. Oh, I missed the question, sorry. Just to clarify, -3 line and 1 line are 0 because the derivative of them is 0. Everything in the table now refers to the derivative at the top of the screen there. The original function is out of my mind for a second until I come back to the sentences. So I have zeros on the lines because the derivative function, see here, derivative, is 0. So the table is done for the derivative, even though I'm using that information ultimately to make a statement about the original function. So I'm sort of temporarily looking at different things. And so I can conclude the original function is decreasing on -3 to 1. Include because for both of them, they sort of have an overlap at 0. And 0 is okay for either one of them, sort of where the windows are attached to each other. Yeah, definitely interrupt at any stage. Any questions? There's always something new and something I need to look at in the right way, and people get confused. When do I look at what? I'm not graphing the derivative, yet I'm analyzing it to make a statement about the original function. That's very important. Okay, so if I zoom out and look at this again, my first function should always be a polynomial. It's the simplest one I'm going to have. By finding the derivative, factoring it, and then analyzing that, I prefer the table. It's not a necessity. I'm never going to force you to use the table, but I cannot think of anything that's going to be easier than this table. I still use it all the time. It's so nice. It makes everything as clear as it could possibly be. If I look at the derivative at the bottom of this table here, remembering that the derivative refers to the slopes of tangent lines, right? Positive means my tangent lines are going up. I don't know how exactly. They're going up. I just have a general, just going to have a general upslope. Then 0 is going to be horizontal tangent line at -3, and then I'm going to have a downslope again. And around this x equal to 1, it's going to go downslope, horizontal, upslope. So these slope lines can give me a picture of what's happening to the graph. It's going to make a little crest, and then a little cup, a little dip in the graph, and that's exactly what's happening. Ooh. I guess I can make a new page. I wanted to squeeze it all in here. I guess that's a bad idea. Fine. Again, we don't know exactly what the graph looks like, but the picture is definitely forming. So if I set this up, I would, at this stage, if I wanted to graph, have the information from step 2, which is, oopsie, not that one, 4 for the y-intercept. Maybe 4 sits over there. That's the information I would have coming out of step 2. Now I have some more information. That something interesting is happening at -3. And on the way to -3, which let's put -3 over here, I'm increasing. But there's a point sitting at -3. Where is it? Is it high? Is it low? I don't know. I need to find the y values. I need to find the y values corresponding to these x values. So it's a little tedious, to be fair, but we can quickly do it. It needs to be done, so let's do it. So I want to know what is happening at -3. I can't type in my calculator and speak, so it might seem a little quiet for a second. So I have -3 cubed is -27 plus 3 times 3 squared is also going to be 27. Oh, that's easy. Then two negatives will be another 27 plus 4. Looks like 31. Correct me if I'm wrong. I'm trying to do this fast because we have a lot of functions to get through. And we are, strangely enough, behind schedule. It's weird. Check the other one. Should get a -1. That now tells me where these guys sit. So the first one actually sits super high. I'm just going to put it up here at 31. What's happening there? A little crest. Whoopsie. At least touch it. A little crest is happening there. I'm just drawing it to remind myself. It might not look exactly like that. Then something's happening at 1. Let's put 1 over here. And my point is actually quite low at -1. And what's happening there is a little cup. So you should see how the shape is starting to show now. I'm going to go up, turn, go down through, not straight, curvy, go down through the y-intercept, and then go up again to infinity. See how that familiar shape that you have seen in pre-calculus, that N shape, is starting to form. And the increasing decreasing behavior is a big step forward into filling in the graph and adding pieces to the puzzle. Okay. Now for a simple polynomial like that, you can probably have a pretty accurate graph at this stage, but in some other cases it's still not going to be perfect. But that is a discussion for later. Exactly what's missing, why there's a step 4, and so on. Okay, so that was a polynomial. Let's see a rational function. And I don't want to make this function overly complicated. Actually, something that you could do transformations on and figure it out that way. We are now having more sophisticated tools to not rely on transformations because not everything can be done with transformations of basic functions in an easy way. That's the good thing is that this isn't a difficult function, that I could sort of guess what this is. The downside is that if I have to find the derivative, this is going to be a quotient rule, unfortunately, which in application isn't terrible. The bottom squared, derivative of the top times the bottom minus the top times the derivative of the bottom. I picked easy polynomials, so this derivative isn't terrible. Let me just, actually, I don't want to do it there. New line. Then I have here, these ones don't actually matter, right? I want to show them when I find the derivative to show that I've used the quotient rule completely, but in simplification, they don't actually matter. I have an x here, I have a minus x, so there are no x's. I have a 1 and a plus 1, so it's a 2 over x plus 1 squared. And now I have a reason to simplify this, because moving to my table, I need to see which pieces are actually being multiplied or divided here. Regardless, I have the derivative equaling 0 when? When is this derivative going to equal 0? For which x values? That is my question to you. Which x values will make that derivative 0? -1? Plug in -1 into the derivative. What do you get? Put it into your calculator. Let's do it. 2 divided by -1 plus 1 bracket squared. Bad times, bad times. Undefined. Because when I plug in -1, I'm dividing by 0. So yes, there is another one here. Whoopsie. There is another one that I need to take note of. And that is where the derivative is undefined. That is going to be when x equals -1, when the denominator equals 0. To make this answer, the derivative y value 0, I need the numerator to be 0. And in this case, that is not going to happen. Numerator equals 0. Not going to happen. But I need to look, right? So I have 2 of them now. I have to check where is the derivative 0. Okay, in this case, the numerator doesn't have an x in it, so never. But there are still interesting x values. And those are the ones that make the derivative undefined. So the polynomial didn't give me the full picture. There's more here that I have to check. Where is it 0? Where is it undefined? But of course, in the case of a polynomial, it's never going to be undefined. In the case of the rational function, it could be. Regardless, out of these 2 checks, and it's only going to be these 2, 0, undefined, I am going to list all the x values that come out of that. And in this case, maybe a little boring, it's only one of them, only the -1. Regardless, a simple table is just better. I'm listing everything. The 2, and there are 2 x plus 1s. And my interval is only split up into 2. Sorry, my x values are only split up into 2 intervals. There was only 1 x value that came out of this. They're going to combine to give me the derivative. Now 2 doesn't do much, but it is there. I don't want to miss it. It's always positive. X plus 1 is 0. When x is -1, it's going to go negative to positive. And because I get these simple pieces, x plus or minus a number, it looks like it's always negative to positive, but definitely check. Be sure. This second x plus 1 is exactly the same. Yes, I could have grouped them, but then I deal with something squared, which I need to slow down and think about. Having simplest possible pieces, even if they double up, just makes it easier. So now I have a different situation. At x equal to -1, the derivative is undefined, not 0. To the left, I have a positive and 2 negatives. My answer will always be positive. To the right, I have all positives. So if I look at the slope lines, it's going to go positive, something is going to happen, and then positive again. It's not quite clear at this stage until you bring in what happens from step 2. But before we do that, let's just write down our sentences. My function is increasing on. Now I can't say everywhere. That is not right. Why? Because when I look at my function, which is what the statement is saying something about, this guy is undefined at x equal to -1. So I can't ever include -1 in any statement like this, because there is no point to compare. So I need to make sure that -1 is excluded from this set of x values. So -infinity to -1, round bracket. There is no point that I can have at -1. And also, I'm going to use the union symbol because I have to be proper, but you don't have to. -1 to infinity. So it's everything except -1. Now, when we see more examples, the little things that you have to keep in mind will become more clear. But I'll just emphasize again, it has got nothing to do with the table. It has got everything to do with the function. The fact that the derivative is undefined is irrelevant. It's the function that is undefined at -1. That is why I'm excluding it. So you have to always remember that the statements ultimately that I'm trying to make are in reference to the original function. Always glance back. Have a look. What is my original function? Does this statement make sense? Because often the derivative doesn't know what you're trying to do. It's just saying, here I am. This is my property. Do with that what you will. I have to think about, well, what am I doing with that? Look back at the function. That is what I'm saying something about. Now, if you want to graph it, you would have done step 2 first. You would have done asymptotic behavior first. And we would have seen there's a horizontal asymptote of 1. There is a vertical asymptote of -1. So you would have already had some graph information. Let's fill in what it would have looked like after step 2. We would have found our vertical asymptote. We would say, well, it's one of those two. It's one of those two. Don't really know, don't really care. Step 2 is only some of the puzzle pieces. We would have had a horizontal asymptote. It approaches it in some way. It approaches it in some way. I don't know. Don't really care either. And we had a y-intercept, right? Y-intercept, when I plug in a 0, I get -1. So that would come from step 1. I'm just going to put it a little bit higher than usual. Forget the scale. Okay, so this is what we have after step 2. And of course, you've practiced. We've done a lot of these. This should be quite straightforward, especially for a simple function like this. No real work was required. Now, we have some extra information that the derivative gives me, that it's undefined at -1. Well, of course, there is no graph at -1. There's no point. How can there be a slope of a tangent line when there is no tangent line? There is no line to be tangent because there's no graph, because there's a vertical asymptote. So what I find from the derivative agrees with what I have so far. Now it says I'm increasing everywhere else. Everywhere there's a graph, I'm going up. I'm going uphill. Now look at this. If I take this bottom arrow as my choice, I'm going to go downhill. And that is not happening. So the only way for me to go uphill always is to come to the horizontal asymptote on the left from above. I'm going to go uphill to the top arrow of the first two. Then I need to go uphill towards the y-intercept. I can't have this top arrow anymore. It has to come from the bottom through -1. I can't be doing this because then I would have a downhill section, and that never happens. So I have to come at the horizontal asymptote on the right from below. And this is why I said last time that once we get to step 3, choosing which arrows are correct is quite straightforward. It's all because of the increasing and decreasing behavior. There is only one arrow in each case that could possibly work. I don't have to make that choice early and figure out which arrow is correct, because when I come to increasing, decreasing behavior, it's going to follow right away. Now all I have to do is make a graph that is reasonably pretty. Because this one is so simple, there's not much missing here. And I can just fill it in. I have to make sure I hit this y-intercept very well without being too wobbly. Ooh, what happened there? Nothing happened. There we go. All of the pieces work together to form the picture, to form the graph. And in this simple case, that was pretty much all I needed. All right. How do we feel about that so far? There's a lot of things to do. We can't skip a lot of examples. We need examples to see all there is to see. And if it takes us a little longer, it takes us a little longer. Now, of course, we need more examples. I have a couple more to do, but we have to pause it here and then pick it up again tomorrow, and it takes as long as it takes.